All right, so for the last talk of OBTS 8, we are going to be talking about Dylib hijacking. Now, the reason I get to go last isn't for some great thing. It's really just I put off my slides to the very end, as Andy can attest. So I figure if I go last, I have all the time of the conference to fit. So today, we are going to learn about Dylib hijacking, and more importantly, the mitigations that Apple has introduced to comprehensively thwart this threat. We need to establish a few definitions before we dive in. So first is, what is a dependency? A dependency is a library a program relies on, or depends on, in order to run. We'll also talk a lot about the loader. In this context, the loader is simply a program that loads an executable into memory, prepares it to run, and then transfers control to it. On macOS, we refer to libraries as Dylibs, and the loader I refer to as Dylb. My name is Patrick. You probably know me already, mostly in the context of the Objective-C Foundation. Also recently, I have co-founded W, where I work with my amazing co-founder, Mike S. We are building core macOS detection components to integrate into larger macOS EDR security products. All right, let's start with a brief introduction and some concepts. First, let's talk about processes, really in the context of them being trusted entities. So I'm sure you all know that process runs in an isolated address space that includes the main application binary or program binary, and also any of its libraries or dependencies. Now, the most important thing for the context of this talk is that security decisions are made at the process level. And that is also extended, therefore, to any libraries, any dependencies that are also loaded in that same process. On macOS, here are some of the process-level security decisions. For example, entitlements are applied to the process, but then are applied to anything loaded in the context of that same process. Endpoint security events, we will see, are tied to a responsible process. Resource access, like TCC checks, are done at the process level. And then we'll also see a lot of security tools make decisions based on processes. So, no surprises, you might be wondering, okay, I understand that, but what does that mean if we can somehow inject a library or malicious code into what is otherwise a trusted process? Well, kind of game over, because as I just mentioned, any library within the context of a trusted process really inherits that process's same amount of trust, which for the security decisions we just saw is very problematic. Now, there's many ways to do that. We're going to focus specifically here on Dylib hijacking. Now, Dylib hijacking, or more generically, library hijacking, has a very long history. So I think it's very important for us to first start by talking about that. So it starts all the way back in 1998, where everyone's favorite intelligence agency, the NSA, actually publicly released a document talking about this very issue on Windows. A few years later, an individual kind of noticed this and posted a blog post about it. Really wasn't picked up until 2010, when H.D. Moore really made a public discovery, and Microsoft published, which is now a very much referenced security advisory talking about library hijacking on Windows. Fast forward 5 years later, I remember explicitly I was sitting at a gate waiting for a plane to take off, and I was like, wait, Windows is vulnerable to library hijacking. I wonder if macOS is vulnerable as well. So I dug into the macOS loader, and turned out it was, and so in 2015, I gave some conference talks and some research papers on how macOS was also vulnerable to library or Dylib hijacking. Since then, Apple has introduced a myriad of mitigations that we will look at, which really aim to thwart, kill, unalive Dylib hijacking. So, how are processes launched? This is kind of review, but the idea is the user double-clicks a process, or a system process spawns a child process. Behind the scenes, the loader, Dylb, gets involved. It takes the binary from disk and loads it into memory, which also includes loading any dependencies that the process has. So the next question is, how are these dependencies specified? Well, on macOS, it's done via something known as load commands, which are directly in the main application binary. We can use macOS's O tool. If we execute it with the capital L flag, it will list us all the dependencies that a program has. So for example, we do that with calculator, and we can see the absolute paths to the libraries, the dynamic libraries that calculator needs in order to run. If we execute O-tool with the lowercase l, we can actually see the actual load commands, and we will see there is an lc underscore load underscore dylib load command for each of the dependencies. Basically, what the loader does is just iterates through the mock-O, and anytime it finds a dependency, it will load that into memory as part of the loading process before it hands off execution to the process. Now, this is also relevant for us in the context of malware analysis. Those of you who took my training, we talked a lot about how dependencies can give us insights into what a program is doing. So very briefly, as a tangent, imagine we have a malware sample such as MOX. We can see it has some very interesting dependencies. For example, it is linked or depends on core WLAN because the malware did Wi-Fi scans, and core WLAN is Apple's library that provides this capability. Similarly, AV Foundation, the malware used this to talk to the mic and the webcam to spy on the user. And finally, disk arbitration is the Apple library that you can link against as a dependency if you want to do things like monitor USB drives for files to exfiltrate, which is exactly what the malware did. Now, an observation, so far all the dependencies we have seen are absolute. They are system binaries. But what if an application has what I refer to as an internal dependency? So on the slide, you can see we have an application bundle, and in the main executable, here called foo, it has a dependency on its own library that's in the framework directory. Now, you could pretty clearly see that if we have an absolute dependency on this, this is going to be problematic because what if you install this application in /applications, but I try to run it from my desktop? Those are two different paths, and so absolute dependencies aren't going to work in this case. macOS's solution is to provide us, software developers, with something called run path dependencies. And if we dump an application that has a run path dependency, we can see two things. First, its relative dylibs, its relative dependencies are prefixed with @rpath. This is a special keyword to the loader. And what the loader does at runtime, it replaces these with a certain number of run path directories. There is another new load command, which is the lc_rpath load command, and this specifies the run path directories that the loader should look for. So in this case, this application has one that is in the executable's location, also one that's relative in the framework directory. The key thing is this allows for relative dependencies, but a takeaway is that the loader, DYLD, is going to search each of the run path directories and unfortunately blindly load the first dylib it finds that matches the dependency's name. So this allows us now to understand and define what I mean when I'm talking about dylib or library hijacking. So imagine we have an application or a program that has multiple run path directories, and that the legitimate dependency, the one that ships with the application created by the original developer, is not found in a primary location, but rather in a secondary location. What this means is we can simply drop or plant a dynamic library that matches the name of the dylib that it's looking for without having to actually modify the binary at all. So here's an example. The app is looking for foo.dylib. The legitimate dylib lives in the second run path search directory. But if we come along and plant our own dylib that's also called foo.library in the primary search path directory, the next time that application is run, the loader is now going to find our dynamic library first, and because it matches the name of what it's looking for, it's going to blindly and naively load it. So this is what Dylib hijacking is, and in 2015, it was just like shooting fish in a barrel. Because what we could do is all sorts of really fun things. First, everything was hijackable. There was a myriad of apps and programs that were vulnerable to this sort of attack. These include, and this is just from my box in 2015, Apple programs, third-party programs, all sorts of stuff. This was also far before Apple mitigations like notarization, library validations, things that we will shortly talk about. So this basically meant if an application was vulnerable to a Dylib hijack, you could very stealthily and very effectively inject code into it. So for example, Xcode was vulnerable to a Dylib hijack. It meant a local attacker could place a specially named dynamic library and get loaded into the context of Xcode, meaning you could do all sorts of funky things like perhaps infect applications that the developer was building. This also provided a very stealthy persistence mechanism. There was a number of Apple programs that would automatically start every time the box was rebooted, and they were susceptible to Dylib hijacking. So we could plant a specially named dynamic library, and every time macOS launched and the application from Apple was run automatically, the loader would naively load our dynamic library, giving us a very stealthy persistence in the context of a trusted Apple process. My most favorite was this really opened a wide range of gatekeeper bypasses. We could do things like find an application that would look for dynamic libraries outside its application bundles, craft a disk image like we see on the slide where the trusted application was there, but also the external directory structure. And we could inject a dynamic library there that would essentially be loaded into the context of the application when it was run by the user. Gatekeeper only checked the main application, not its external hijackable dynamic libraries, and so we could sidestep Gatekeeper very easily. Now, one important thing to note, and I was looking for an example of this when I started my slides a while ago, and luckily like a week ago, I stumbled across the perfect example. So what I'm trying to point here is that just because an application or program is vulnerable to Dylib hijacking doesn't necessarily mean it's a security vulnerability. So here's an unfortunate counterexample to that. There was a posting on Twitter about a week ago, and it said millions of Windows users are vulnerable to this brand new CVE. Like, this sounds scary. No. All it turns out was Notepad++ on Windows was vulnerable to a library hijack. And it's like, okay, yes, you could get a library loaded into Notepad++, but like, so what? So really, a Dylib hijack or a DLL hijack on Windows is only useful if the target program is trusted, has some additional privileges, or does something useful. All right, so let's talk about Apple's mitigations, because in 2015, we had a big problem. We were stealthily persisting. We were injecting into all sorts of trusted Apple processes. We were sidestepping Gatekeeper, really, really problematic. So first, they introduced a very quick fix. I'm not sure this is actually still in macOS, but what they tried to do is limit the fact that when a user downloads an application bundle, if it references something external that you could also plant, for example, on a disk image, it shouldn't load that. So in 2015, when Apple pushed out this patch, I reverse engineered the XProtect framework and saw what they did. They basically added 2 checks that say a dynamic library has to A, be a trusted system one, or exist within the context of the application bundle. And this was a good start, but actually Apple very quickly realized this was really not the main issue. The main issue here, and this extends far beyond Dylib hijacking, was what they referred to as the repackaging problem. They basically said, when the user downloads something and double-clicks it, maybe we, Apple, have verified that application that the user is running, but there's no way for us to verify everything else on the disk image. It might be an external dynamic library, but it also might be a config file with shell commands, right? We've checked perhaps the application bundle, that it's notarized and signed, et cetera, but Apple understood that they cannot really protect against relatively external content, anything else on that disk image. So what they did to actually protect against the wide range of attacks is introduce something that I refer to as translocation, but Apple calls it gatekeeper path randomization. So let's walk through this, and the diagram on the slide really, I think, explains it well. So imagine the user downloads a disk image from the internet, or a zip file. When they go to extract it, there's a few different items on the disk image. The user's probably going to click the main application bundle, and what Apple has to do here is somehow protect the user from all of the external content that is on the rest of that disk image, which may not be validated. So what Apple actually does is, when the user double-clicks on that application bundle, they go and make a copy of it in a protected, isolated directory. And the key is here, any references then to untrusted external content on that disk image are broken, because Apple has moved just the application bundle and left everything else over here. So we can see this in action. If you download anything from the internet, double-click it. If you run a file or process monitor, you can see this app translocation happening. You will observe Apple, macOS, taking the application bundle and copying it to a read-only, randomly named location that has app translocation in its path, and then running the application from then. And again, the only thing that's copied there is the application bundle. So this is great because Apple really has kind of severed any reference to external content, either hijackable dylibs, config files, other applications that are on that disk image, and are really only running what they have verified and what the user wants. So really good job there by Apple. Apple also introduced notarization. There's been a few talks explaining what notarization is, so I won't go over that here. But the idea is, even now, if I take a vulnerable application and add a hijacker dylib, and then deploy that to users, even if macOS would be tricked into trying to load that dynamic library, macOS will be like, hey, wait a minute, the injected content is not notarized, and it will block this. So notarization also comes into play here as well. Now, the best mitigation I think Apple did was to introduce something called library validation. So when I was talking about this issue in 2016, almost a decade ago, I said, hey, Apple, you know what? I have a suggestion for you. Why would applications ever load a library that doesn't belong to the main application developer? For example, my Objective-C tools. Why would Lulu ever run a dynamic library that doesn't belong to either Apple or the Objective-C Foundation? And Apple, in 2018, kind of listened. They probably had this idea as well. And so they implemented the hardened runtime, which enforces something called library validation. Basically, it says that an application can only load dynamic libraries if A, it's either signed by the same developer as the application, or B, signed by Apple proper, meaning it's a system library. So this means even if we have now a vulnerable application that's vulnerable to a Dylib hijack, if Patrick comes along and tries to plant a dynamic library, library validation is going to be like, yeah, no. Like, this is something different. This is an untrusted dynamic library. I am not going to load that. And then finally, in the last few years, Apple also improved both TCC and Gatekeeper, and there were some mentions of, in talks earlier today about this, that really shows that even if you somehow could bypass all those other mitigations, that at runtime, Gatekeeper will actually revalidate the integrity of an application. So even as a local attacker where notarization normally doesn't come into play, macOS will now actually revalidate the application bundle. So if you try to inject a dynamic library into something that's vulnerable, when the user goes to double-click it, macOS will revalidate the app bundle, see that someone has tampered with it. The code signing information will obviously be broken, and that's a problem. Also, TCC now protects applications, so even if I'm a local user with root privileges, I would not actually be able to write to the application bundle. So let's start wrapping this up. So key takeaways. Dylib hijacking on macOS was a massive security issue in 2015. You could do all sorts of things. But Apple, to their credit, responded quickly and resoundingly. They introduced notarization, translocation, library validation, and app protection, including TC and gatekeeper checks. So RIP to Dylib hijacking, unfortunately. But is it really dead? Ta-da. No, of course not. So let's talk about Dylib hijacking on macOS, and we'll see that what we have to do is sidestep many of Apple's mitigations. Again, our goal is to somehow find a vulnerable application, plant a dynamic library, and then gain all sorts of trust by exploiting this. So first, let's talk about bypassing translocation. I'm not sure if this is known, but it was shocking to me because it really is a way for us to completely sidestep Apple's translocation totally. So again, remember the way app translocation works. User downloads something from the internet on a disk image or in a zip file. They double-click on the main application bundle. Behind the scenes, Apple takes that application bundle, copies it and only it to a trusted directory, and runs it from there so that all references to external content are severed. Well, what can we do? Let's build a disk image, put an application and external content, and then hide that, but create an icon that symlinks not to the application bundle, but to the application executable. If you do this, application, for whatever reason, does not apply. I have no idea why. So here's an example of that. I take Photoshop, put it on a disk image, hide it, and then create a symlink, which is that icon on the top that looks like Photoshop. It has the little like arrow icon showing it's a link, but average user's not going to really think anything of that. And that symlink does not point to the Photoshop application, but rather the application binary. So contents macOS Photoshop.app, or just Photoshop. Download this from the internet, double-click it, and we can see that, unfortunately, Apple is not app translocating this item anymore, but instead runs it directly from the disk image, which means any external content we can still reference. Yikes. So what can we do to exploit that? So what I would do is, because we still have to deal with notarization, is first create a benign application that has a dynamic library that does something interesting. For example, downloads and executes in-memory payloads. Let's submit this to Apple, get them to notarize it, because we're not doing anything suspicious yet. Then take that now notarized dynamic library and package it up with a trusted application that has a vulnerable Dylib hijacker. Now, fair point, this is a little convoluted in a lot of steps. I did mention that app translocation tries to solve a bigger problem, which is referencing any external content. So actually what I would do in this case is something a little bit more basic. Really now, anything that loads or runs external content that's normally blocked by app translocation is fair game, even on macOS 26. So for example, let's create a very simple application that at runtime looks for a config file in its working directory that contains shell commands. Let's submit that application to Apple, but leave out that config file. Apple is going to notarize that because the application doesn't do anything harmful. We then package that up on a disk image, plant the config file next to the application, and use our symlink trick. If we didn't use the symlink trick, the app would be copied to a trusted location, the config file would be left, and we wouldn't be able to reference it. But now, since application doesn't apply, at runtime, our application, which is now running directly off the disk image, can load that malicious config file that we've added that Apple has never seen before and would never notarize, and we're off and running. Is this a gatekeeper bypass? Maybe. Apple's offering now up to 100,000 for gatekeeper bypasses, so one of y'all should look into this a little more. All right, let's now talk about local hijacks. And I will caveat that there are some Apple mitigations that we will have to sidestep. But let's first talk about how to find applications to see if any are locally hijackable, and then how to create a hijack DLL, and then see if we can bypass Apple's mitigations. OK, so how do we find vulnerable applications? Recall that we need to look for an app that has several prerequisites. And unfortunately now, because of Apple's mitigations, we have to add a few additional steps. First, we can only hijack third-party programs. Apple did a really good job shutting down Dylib Hijacking in the context of platform binaries. We have to find an application that has a RPath dependency, a relative dependency, has to have multiple run path directories, and a dependency, a legitimate dependency that's found in a secondary search path. And then finally, because of the hardened runtime that Apple did a really good job on, we have to find an app that is either not compiled with the hard runtime or more likely has an exception that says, hey, I can run any dynamic library. So in 2015, I released a tool called Dylib Hijack Scanner that implements these exact code. So I made a few updates, but it's still essentially the same. And if we run this on a system, on my macOS box, macOS 26 box, there's actually a bunch of legitimate third-party apps that are still vulnerable to Dylib hijacking today. And we're going to pick the first one, which is Adobe Photoshop. This is something that's always running on my system. It has a lot of TCC permissions. It talks to the internet. It's a really good, juicy target. If we use O-tool with the lowercase l flag to dump the load commands, we can see it conforms to what we're looking for in terms of being vulnerable to Dylib hijacking. Specifically, it has a run path dependency on a library called libtbb 12.6.dylib. And looking further, we see it has multiple run path search directories. The legitimate libtbb, which I have no idea what it does, exists in the framework directory. But because of the way the order of the run path search directories, the loader will first look in content/macOS for this library. Also, Photoshop has disabled library validation. So this is all looking good. Now, there's a few things we have to do to craft a compatible hijacker Dylib. This applies to any apps that we are targeting. First off, the dynamic library has to match the exported dependency that the application is looking for. And more importantly, the exports have to be taken care of. Because think about it, why does an application have a dependency? It needs some functionality that that library implements. And so if our hijacker library doesn't implement those expected dependencies, the loader is going to be like GTFO, and actually will crash with a message saying, like, I couldn't find the library that you specified that contains the exports you need. So it's really easy to set the correct version and name, so it would get loaded. The exports turned out to be a little bit harder, but still, there's a really neat trick. So if we dump the dependencies, for example, from libtbb, there is a vast list. And we don't want to have to re-implement all of them. That would take a ton of work. But again, somehow they have to be exported back to the main application so that the loader will load it. Well, it turns out that on macOS, a library can say, hey, I know you're asking me for an export. I don't implement it, but I can tell you who does. And so we can use what is known as a re-export directive and basically tell the loader, yeah, we don't have the exports, but the original libtbb does. And so when we do that, we can now, anytime Photoshop tries to load our hijacker dynamic library and resolves the dependencies it's need, we can tell the loader, yeah, we don't implement it, but go ask the original TBB that's sitting one directory over. And this all magically works. So here's now what we would do to infect Photoshop. You can see in the frameworks directory is the legitimate libtbb. We have planted or dropped a same-named dynamic library with a re-export to the original one in the macOS directory. And this is because, again, the primary run path for Photoshop is content/macOS. So the loader is, unfortunately, well, for them, good for us, going to look for libtbb in macOS first. Now, we run very hard into two things, TCC and gatekeeper checks. So first, TCC says, no, you cannot access Photoshop once it's in the application directory, because that's not good. And so we can see at the top on the slide, even if we have root permissions, if we try to go and plant our hijacker Dylib into Photoshop, it is blocked. Well, it turns out there's a really easy way to sidestep that. That is just make a copy of the app in temp, add your dynamic library there, and then copy it back to applications. Like, duh. For whatever reason, TCC is OK with this. You might need root privileges to copy it back, but this totally sidesteps all of those app protections. And I don't know if Apple is OK with that, because as soon as we launch the application, our friend Gatekeeper comes along and says, OK, this is a new application. Yes, maybe you've subverted it. I don't know. What I'm going to do is I'm going to revalidate the application bundle because, Photoshop is notarized, and if someone has tampered it, we should detect that. So here we are. We're going to show a little video, and we're going to see this, unfortunately, come into play. So what I've done is I've copied the subverted application from the temp directory where I've planted my dynamic library, hijacked Photoshop, back to applications so that the user could rerun it. I'm also going to show you that I can't access this secret text document, just to show you that this terminal does not have full disk access or anything special. So let's see. OK, we can confirm we don't have access. We're going to open the application. Immediately, macOS is going to say, hey, this is a new app. This is a problem. I'm going to verify this. Photoshop is notarized. You cannot just inject a dynamic library and let it load. Like, I'm going to tell you to take a big hike. Wait, what? Nope. Really? Awesome. So our injected library is loaded. We can see we can access all the TCC protected files that Photoshop can because we are loaded in the context of Photoshop. I have no idea why this works, meaning what we are sidestepping, but clearly this is vibe coded. Like, what we are new, Photoshop is notarized, like, Gatekeeper, you had one job. But apparently, in this case, no problems. So what do we have now? We have a very stealthy implant that is pretty persistent. At least on my box, I'm always starting Photoshop. This means that our dynamic library is always loaded within the context of Photoshop. It is able to access any files that Photoshop is allowed, which on my box is basically everything, right? You're exporting files, loading documents, photos, all sorts of stuff. And as I mentioned, because security decisions are made at the process level, because we are loaded into Photoshop, we inherit all those same permissions. There's no impact to functionality. We've re-exported everything to the original libtbb, so that's off and running. Photoshop is not broken. The user sees nothing amiss. And also, if there are security tools, as we'll see, well, let's see. All right, so macOS clearly, like, I don't know what it's doing, but it allows us to do this no problems, which to me is not ideal. So, okay, third-party security tools. They got to be our help, right? So let's first look at Lulu. Lulu is an open-source firewall I create, and Lulu's rules are done at the process level. So on my box, I have a firewall rule saying that Photoshop is allowed to talk to the internet because updates, generative AI, et cetera, et cetera. Lulu's not dumb, though. It says, look, if someone tampers with any process that there is a rule, I'm going to try to detect that and block that. Because it's a very well-known trick back in the day. You find a trusted application that is allowed to talk to the network, add some malicious code, and bypass it. So Lulu does what Apple recommends, and that is call their code signing APIs to first validate when a rule match, does the code signing information of that process still hold, or is something wrong? And here's actually the code signing information that Lulu, I don't show all the code signing APIs, but it does it in the recommended way. Unfortunately, Apple's runtime code signing APIs appear to be limited to the main process. They take into no account any of dynamic libraries, so this means the code signing subsystem comes back to Lulu and says, yeah, Photoshop's good, nothing's been tampered with. And so Lulu's like, okay, I'm going to allow this network connection to go out. All right, what about endpoint security? We've heard a lot of talks about endpoint security and how it's the bee's knees, to use a phrase coined earlier. And yeah, I'm a big fan of endpoint security, but the problem is its granularity only goes down to the responsible process. So, for example, when our injected dynamic library tries to access a TCC-protected file, yes, if there is an endpoint monitor, it would see the file access, but it doesn't identify the dynamic library. It just says Photoshop is accessing a file. So that's kind of problematic because we need more granularity. The last security tool I want to talk about is Santa. And I'm really not picking on Santa here, other than it's arguably the most pedantic security tool I know. It uses a allow list model that basically says, I'm not going to let anything run unless you've explicitly allowed it. So I installed Santa with a pristine version of Photoshop. I created a allow rule based on the team ID, which is what the Santa documentation recommends. And then I hijacked Photoshop and reran it, and we can see that Santa's like, yeah, that's okay. So clearly, like, we could be as naughty as we want, right? And again, I'm not picking on Santa here. Santa's probably doing what Lulu is, which is asking the code signing runtime, hey, is this process still validly signed? And Apple's like, yeah, looks good. So let's talk about some detections, because I don't like to break everything, and then I don't like just being part of the problem. I want to be part of the solution as well. So let's first start talking about static detections, because it's actually pretty easy to detect Dylib hijacking. All you really have to do is scan applications or programs, and if you encounter multiple instances of a run path dynamic library, the app may be hijacked. Like basically, if you see two Dylibs with the same name in an application bundle that have different code signing information, that is a huge red flag. So the DHS, the Dylib Hijack Scanner utility, actually implements this, and if we run it on a box where I've hijacked Photoshop, it pretty easily says, hey, wait a minute, there are two libtbbs in the application bundle. One is signed by Photoshop, the other is like unsigned, not good, this is probably hijacked, and in this case, it is correct. What could security tools like Lulu and Santa do? Yes, there are code signing APIs that allow you to check the contents of an on-disk application bundle. And if you call that with the right flags, it will scan the entire application bundle. So one of the tools I write, what's your sign, does exactly this. If we now examine the code signing information of the Adobe product on disk, it says, yeah, there's a code signing information, right? Photoshop should be signed and notarized, no issues. But as soon as I inject something into its application bundle, if I verify the entire application bundle, that's a problem, and the code signing APIs pick it up. The problem is this is very slow. This is kind of like what macOS wants to do once, and this is why you see that like verifying Photoshop at the beginning. Somehow macOS gets it wrong, as we saw. So this just isn't really a feasible solution for something like Lulu or Santa, because imagine every time Photoshop is run, the security tool is like, okay, hold up an entire minute, I'm going to validate that. So unfortunately, this isn't necessarily an ideal solution for security tools that need to do runtime process checks. Now, there are some opportunities for runtime checks. Unfortunately, If you're Xprotect, you can examine loaded processes, but if you're a third-party security product, you cannot. Apparently, Apple thinks this is something we don't need. I would argue otherwise, as would Matthias, but Apple doesn't often listen to us. Yikes. So with VMMap, though, it has the necessary entitlements to look at memory mappings of arbitrary remote processes. So we can use that to see memory mappings. And if we run that against Photoshop, for example, we can see that there are multiple libraries with the same name. There's basically a name collision in the Adobe Photoshop process space. That's kind of strange. Of course, as Ko talked about in his talk, once you're loaded, the hijacker library could do all sorts of funky things. For example, use a different file name, unload, and use a reflective loader. So again, this technique is lacking. All right, so some conclusions for real this time. So is Dylib hijacking dead? No, it's down, but it's not out. Unfortunately, we are limited to third-party apps that have either not been compiled with a hardened runtime or have opted out of library validation. And there's still a decent number of apps to be hijacked. Now, yes, I like picking on Apple. I love being on stage and pointing out flaws. It makes a great, interesting conference talk. But as a Mac user, it really bothers me that apps on my personal laptop are hijackable. Like, if I could hijack it, that means that other remote attackers, who are probably more sophisticated than me, could as well. And the problematic thing is, Apple is, like, so close to fixing this. So first, like, fix app translocation. I have no idea why this is still broken in 2026, right? The symlink trick just bypasses it completely, and that's a silly trick. So why not just translocate any downloaded binary? So hopefully they fix app translocation. And secondly, like, app validation, why is this broken? Apple, you have one job. You should be able to, given an application bundle, verify that it's still validly signed. Now, they kind of get it right. I tried to hijack some other applications, and in that case, it was caught. So I don't know if there's something specific to Photoshop, something to dig in more. But really, I thought that was going to be the mitigation that would block this attack totally. And if that was the case, I wouldn't be here talking today. So Apple, please get that right. So that is a wrap. There's some resources. This is a topic that we could talk about for hours. So I wanted to give some links if you want to read more. My original research, and there's been some other new information about that as well. So that is a wrap. Again, Dylib hijacking, down but not out. And Apple, like, do your job. So we have a few minutes before we wrap this up. So are there any questions about Dylib hijacking, Apple's mitigations, ideas for infection, anything else? Yes, Matthias.
Did you check how this translates to iOS?
Great question. Did I check how this translates to iOS? I'm gonna let you in on a little secret. iOS to me is too hard. So on macOS, which we unfortunately see as lots of vulnerabilities, I often don't go to iOS to test. I don't have a research device. I don't have a jailbroken device. I should probably chat with you and give you, heads up on some of my bugs and see. In the past, sometimes when I report things to Apple, they patch it, and then there's a CVE on iOS as well, and I'm like, cool, kudos. But no, I haven't looked at this on iOS. The code signing stuff would be super interesting, so we should chat more. I can give you a proof of concept of the application bundle that somehow bypasses this check, and then, something to dig in. Because code signing issues are arguably very problematic, and in the past have led to larger exploits. So let's chat. Great question. Anything else? Okay, awesome. Woo.